Okay, the last video on eigenvalues and eigenvectors, we are looking at applications of eigenvalues and eigenvectors. It doesn't mean that we'll never talk about it again under linear algebra, right? But like the core set of videos on eigenvalues and eigenvectors ends with this talk about applications of eigenvalues and eigenvectors. Okay, so we're looking at some of these applications in the areas of dynamical systems, which I'm very passionate about. Interestingly, I think our next playlist is going to be on dynamical systems. So if that's your thing, so you want to watch out for that. I know for after this video, I think I still have about 8 videos to go on linear algebra, and then most likely, except something else comes up, that I'll be looking at dynamical systems. So, but in this case, we're looking at applications of eigenvalues and eigenvectors in areas like dynamical systems, Markov chains, and stability analysis. So, introduction, eigenvalues and eigenvectors are fundamental tools in linear algebra. They are used to analyze how systems evolve over time, how probabilities stabilize, and whether systems are stable or unstable. They appear in dynamical systems, Markov chains, and stability analysis. And eigenvectors describe directions of motion, while eigenvalues describe growth, decay, or oscillation. So in essence, you are saying we can see eigenvalues as some kind of scalars, while um, in a sense, right? While eigenvectors are vectors technically, right? So talking about dynamical systems straight up, we look at how eigenvalues and eigenvectors help here. A dynamical system describes how a state changes with time. That's basically a dynamical system. So it's the evolution of a system of a situation over time. So we can have a discrete time system like where you have when something is discrete, it is countable, right? You have x something like x sub k plus 1 equals ax sub k. That's discrete. And you can also have continuous time dynamical system where you have, something continuing like that. You can't really count, right? So everything just flows. So in that case, you have dx dt equals ax, where x is the state vector and a is the system matrix in both cases. So the eigenvalues of a determine long-term behavior. So whatever the eigenvalue of a will be in these situations to determine the long-term behavior of the system, because the system is evolving. So the eigenvalues of a will determine how the fate of the system at the end of the day. Of course, when we talk about dynamical system, it could be anything at all. It could be how blood is flowing in the body, or in the human body, or any kind of system you can model like that. So we talk about role of eigenvalues in dynamical systems. So of if AV equals lambda V, this classic idea that when a matrix rather acts on a vector, the effect at the end of the day is to scale the vector, right? And if that happens, then we can also say that AKV is the same thing as lambda kv. This means that eigenvectors give invariant directions. The directions don't change, right? And then eigenvalues give growth or decay rates, right? So eigenvectors give invariant directions while eigenvalues give growth or decay rates. So if the absolute value of lambda is greater than 1, the solutions will grow. If the absolute value of lambda is less than 1, the solutions will decay. That's what happens for dynamical systems. Then we go ahead to talk about diagonalization method. Now, if matrix A is diagonalizable, then we can say A is equal to PDP inverse. We saw that under, I think, video 33. Yeah, video 33, yes. We saw diagonalization there. Then, and we also saw that if you can diagonalize the matrix, we can easily raise the matrix to any power without going through too much hassle, right? So, and we saw that D is a diagonal matrix which contains eigenvalues, while P contains eigenvectors. So this simplifies computing powers of it. So if you want to compute the powers of a particular matrix, once you can diagonalize it, the whole process gets really easy. I demonstrated that in the video about diagonalizing, that video 33. So now look at this example. So discrete for a discrete dynamical system, imagine that you have x sub k plus 1 equals 3002 xk. Of course, the eigenvalues will be lambda 1, 3, lambda 2, 2. So the general solution then can then be expected to be x sub k equals 3 raised to power k 0, 0, 2 raised to power k, x naught. That's what the system will end up being. And then if we have an initial condition like x naught equals 1, 1, then if you multiply 3k0, 3 raised power k 0, 0 to 2 raised power k by 1, 1, we end up just getting 3 raised power xk will now be 3 raised power k and 2 raised power k. So in those different components. So the interpretation is simply this, that the first component grows faster than the second and the system diverges. So I want to see if I can push down something here to show, because, okay, yeah, this is representing different thoughts. That's why I felt it's necessary to do that. Right. So in this case now, this one is in two components, the X component, the Y component. So the growth is faster in the first component compared to the second component. And as a result of that, the system diverges because, it just grows boundlessly. The first component grows faster than the second, the system diverges. So we look at an example talking about a continuous dynamical system. So given dx dt equals 2, 0, 0 minus 1 x, so the eigenvalues are clearly, because this is a matrix in echelon form, if you like, or it's a diagonal matrix. So you can easily read off the eigenvalues from there. So lambda one is 2, lambda 2 is minus 1. So, and to solve this, you just know that x raised power 2, it will be e raised power 2t 0, 0 e raised power minus t, based on all this, right? So it's more like you have e raised power 2t, e raised power minus t, with an initial the x of 0, the initial situation. So to interpret this, you see that one direction grows. So in this direction now, e raised power 2t grows in this direction, and one direction decays. So that means the two systems can't agree. One is growing, one is decaying. So the system becomes unstable. But of course, the system will tend to move more in the direction of explosion. So the system of it is like explosion, like it's going. The growth is more like faster than the decay. But of course, overall, the system is not stable. Then we talk about another application of eigenvalues and eigenvectors when we in the realm of Markov chains. So a Markov chain models random transitions between states. So let's say you are in a room, and we can actually model your movement in that room over time using Markov chains because it talks about random transition. So let's say that the room is marked, there are 50 spots marked in the room. So what are the chances that you move from any one of the of the spots in the room to another spot? That's the kind of thing Markov chain relates with. So it is written as x sub k plus 1 equals p x sub k, where p is the transition matrix. So just like the A matrix the other time, this is a transition matrix, and all entries are non-negative. So for Markov chains like this, so everything is non-negative. Everything has got to be positive. So each column or row sums to one. It's a probability transition, a probability matrix, by the way. So that's why you don't get negatives because all probabilities lie between 0 and 1, right? Where the assurance, 100% confidence is 1, while 100% lack of confidence is 0. Okay, so every other thing is in between, fractions, decimals, but not between 0 and 1. So each column or row sums to 1. Then the state vector represents probabilities. So this P represents probabilities. Yeah, the state vector represents probabilities generally. Then we talk about the stationary distribution. So you see, for stationary distribution now, a stationary distribution satisfies P of x equals x. You see, this P of x is actually coming from here. So if it's more like some kind of equilibrium. So we say, in that case now, this scale doesn't matter anymore. So we just have x is equal to P of px, right? So in that case, now we can then solve. So this implies that if we have px minus x equals 0, since this is a matrix, that'll be p minus I into x equals 0. So here we see that the lambda, the lambda is 1. So for this now, lambda equals 1 is an eigenvalue of p, okay, for this kind of situation. So lambda equals 1 is an eigenvalue of p. So the corresponding eigenvector gives steady state probabilities. The eigenvector corresponding to this gives steady state probabilities. Normally we'll look for the absolute value of p minus I, right? Here we don't have anything like lambda. Okay, well, I mean, we just have that eigenvalue like that. And then at the end of the day, we have the long-term behavior of Markov chains. If the largest eigenvalue is one, all other eigenvalues satisfies the fact that absolute value of lambda is less than one, then the limit of p raised to power k as k goes to infinity will exist. And then the chain converges to a steady state that you can now guarantee that, okay, the the movement, maybe the person ends up sitting at a particular staying in one particular spot. That's the kind of idea over time, right? So imagine this now. Imagine this Markov chain where we have p is 0.7, 0.4, 0.3, 0.6. So you see 0.7, 0.1, zero point 3 adds to 1, 0.4, 0.6 also sums to 1, like that. So to find the stationary distribution, now we need to solve for px equals x. So p minus 1 x equals 0. So we have, so this is the unit matrix, right? So you have 0.7 minus 1, that's minus 0.3. So 0.40, we have this 0.3, then 0.6 minus 1, that's minus 0.4, x equals 0. So in this case, now we need to find these, the values x and y. So in this case, now we see minus 0.34 plus 0.4 y equals 0. The other hand to same, we have the same kind of thing. So generally speaking, we see that y equals 3 over 4x. So if you choose, so in this case now, if you normalize, you have x plus y equals 1. So since this must happen, right? It is probability we are dealing with here. So x plus y must be equal to 1. So if that is the case now, we already know that y is 3 over 4x. So x plus 3 over 4x is equal to 1. So that means that if you solve that, this is going to be 7 over 4x equals 1, meaning that x is 4 over 7, and automatically y has got to be 1 minus 4 over 7, which is 3 over 7. So in this case now, because we are dealing with probability, this is the kind of thing that happens. So what does that mean? It means that at the end of the day, x is 4 over 7 and y is 3 over 7, like that. So we have that. Then we go ahead to talk about stability analysis. Consider the system x prime equals ax. That's dx dt or dx dy, whatever you like, is equal to ax. The equilibrium point is x equals 0, right? That means ax is equal to 0. So the equilibrium point is x equals 0. Is x equals 0. Stability then depends on eigenvalues of a. So if you talk about stability, it depends on the eigenvalue of a in this situation. So, and we have for continuous systems, for x prime equals ax, right? We have eigenvalues and the behavior. If all the real components of the eigenvalue is less than 0, that'll be stable because real value of real component of eigenvalue is less than 0. That's negative. That means that there'll be a decay, just like the other time you have e raised power minus something. So there'll be stability because to be moving towards something. If any of the real components of the eigenvalue is greater than 0, then there'll be instability. So because even if there's another one that is decaying, then it will still be unstable. Then if you have mixed signs, that'll be a saddle, and then pure imaginary. So if you have imaginary numbers, there'll be an oscillation, right? Maybe some maybe so you have some kind of maybe damping oscillation. You can have what is it can have a sink, it can have a source, and all of these kind of things, even in oscillation. Then we talk about discrete systems. So for x sub k plus 1 equals ax sub k, if you have eigenvalues like this, these are the stability conditions. The absolute value of lambda less than 1 means stability. The absolute value of lambda greater than 1 is unstable. The absolute value of lambda equals 1, that's marginal. That is maybe nothing much is happening, so to speak. So for continuous stability, now we have a is minus 2, 0, 0, 2. So of course the eigenvalues are clearly minus 2 and 1. So you have lambda 1 is minus 2, lambda 2 is 1. By way of interpretation, one in eigenvalue is negative and one is positive. So the answer is that the eigenvalue is a saddle point because and that means that the system is unstable. Just like what we saw the other time. I'm thinking I can push things down here a little bit to just separate them. Yeah, for a bit more to show that the points are not together. Okay, so here we see that this is negative, this is positive. Both of them have to be negative for us to have stability in this case now. So the system is unstable because one is decaying, the other is growing. Then we also have for discrete stability too. So given A is 0.50, 0.8, for the eigenvalues, lambda 1 is 0.5, lambda 2 is 0.8. That's easy to read off because we have a diagonal matrix. So if you check now, the absolute value of lambda for 0.5, it's less than 1. For 0.8, it's also less than 1. Answer, this system is asymptotically stable because all solutions will converge to 0 because the eigenvalues, the absolute value of the eigenvalues are less than 1 in both cases. So overall, the system will go to an equilibrium point. It's a stable point rather. Okay. What if you have complex eigenvalues? So if your eigenvalues are a plus of the form a plus or minus bi, then for if the real part a is less than 0, if this real part is negative, so you have a spiral in that. Spiral in means that you have, let's say you have a point like this. So spiral in means you have something moving from outside and coming inside into that point. That is spiral in. Okay, so that's the way that's going, and that happens for you have a plus or minus bi for a is less than 0. Okay, that's a is negative, so it's spiraling in. So it's oscillatory, but it's going in. Then if a is greater than 0, then it spirals out. Okay, that spirals out. So what spirals out means the opposite of spiral in. So in this case now, you have a plus bi, and then you then have a plus or minus bi, and then a is now greater than 0. See what's happening? You have this point here. So it means this one is spiraling out, meaning out of this place now, you have something growing out like this. So the arrow is pointing out, it's pointing out of that point. Whereas this one is spiraling in. So this is a spiral in, and then a greater than 0. This is a spiral out. Okay. We have the other situation too, which gives us a center, or what I think what is called a limit cycle. So if A is equal to 0, you have a center. What that simply means is this: a center happens when A is equal to 0 for that kind of situation. So you have A plus BI, in fact, A plus or minus BI, and then A is not equal to 0. So you see, the other time you had this point and spiraling out. But here now, you have the point here, and then you have an orbit around it. So there's no spiraling in us or out. So you just have an orbit around it, just moving around it like that. So this is what you call a center. I think it's called a center. I think it's also known as a limit cycle, I believe. I think it's limit cycle. Or if you like, call it an orbit. Okay. So that's what happens in that kind of situation, in stability analysis. So you have this example that lambda is minus 1 plus or minus 2i. Because this minus 1 is less than 0, so the real part is negative, as you can see, then the system is a stable spiral. So it's a stable spiral because it will be spiraling in. So it's a stable spiral. But spiral out is an unstable spiral. So I think we can even say more about this, right? So this is, this will be a stable spiral, you know, this is a stable spiral, and this is an unstable spiral. Unstable because it's spiraling out, so it is growing outwardly. Unstable spiral like that. So for this kind of case now, you have an unstable spiral. So this system is a stable, or this is a stable spiral because of this minus one here. Okay. And it's a spiral because it's complex. It has complex eigenvalues. So we can have a unified view then that so for dynamical systems, eigenvalues determine whether the systems grow or decay. For Markov chains, eigenvalues determine steady state. For stability, eigenvalues determine the equilibrium type. So we see that eigenvectors give directions while eigenvalues give rates. In summary, we see that for dynamical systems, Can I fit everything at once? Yeah, I think it's better to have everything in one blow. So dynamical systems, they are governed by the matrix A raised power k or E raised power at, and eigenvalues control growth. Then for Markov chain, steady state is eigenvector of lambda equals 1. Then other eigenvalues control convergence. Then for stability, real parts and magnitudes determine stability. So when we talk about stability, so you can see stability and dynamical systems are somewhat connected, because by the time I teach dynamical systems, you're going to see the concept of stability is a big deal there. Okay. So check out these problems and try them out. You've seen the how to go about them already. So at the end of, just look for the eigenvalues. The eigenvalues are always obvious here, like 2 0.5. So describe the long-term behavior of this. Well, I mean this system is not going to this system is going to explode because the both eigenvalues are positive, so they are going to. Okay, but then we are talking about discrete. So for discrete, the absolute value of 0.5 here is less than 1, while the absolute value of 2 is greater than 1. So we are going to have instability here. Then coming here, this is discrete, this is continuous. So for this continuous, now we have minus 3 and 1. So this one will be decaying, this one will be growing. So unstable. Find the eigenvalues and determine whether it's diagonalizable. Oh, diagonalization is coming in here. So we have 4, 2. So yeah, this should be diagonalizable because first of all, we have distinct eigenvalues. It should be diagonalizable, I believe. In fact, I think this was exactly what I diagonalized the other time. The Markov in a video, the video under diagonalization, the Markov chain steady state P is 0.5, 0.3. Find the stationary distribution. Of course, you've seen that kind of thing before. Markov chain convergence. Determine whether the chain converges to a steady state. Follow the example like before. Yeah, so just try your hands on this. All these questions. Now we have 6 to 8. Okay, 6 to 8 right here. Try your hands and see how well you can get them. 3 Markov chain. So you want to try this. We've done the 2 by 2 type before. So just try this for this 3 by 3. Yes, with this, I come to the end of this very interesting video about applications of eigenvalues and eigenvectors as we see it in dynamical systems, Markov chains, and stability analysis. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you have not subscribed, I wonder why. Why not just go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That will give you some special privileges, like some materials are made for only you, or you see them first before other people, or you see them exclusively. Nobody else sees them apart from members. You can have access to my PDF notes, all kinds of perks. We can hang out together to discuss whatever interests you on this channel and all that. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.